Hello everyone, my name is Jiahao, and I am from Shanghai Jiao University. It's a great honor to have this opportunity to present our paper, Trajectory-Based Model Predictive Control Strategy for LC Filtered Voltage Source Inverters. And I will introduce this paper from these four sections. First is a brief system description, which mainly reviews the conventional control strategies and introduces the motivation of the proposed control strategy. The subsequent sections elaborate the proposed TBMPC and give the simulation results to show its validity and superiority. The final section draws the conclusion of this paper. Here, figure 1 shows a typical three-phase two-level voltage source inverter filtered by an LC filter and connected with a three-phase load. Since it works in islanded mode, the main control objective is to regulate the output voltage and achieve good power quality. The conventional control structure, like cascaded, proportional, and integral controllers, which is shown in Figure 2. The advantage is obvious that this kind of linear controller outputs high-quality voltage waveforms, but the disadvantages are also annoying, like low control bandwidth, slow dynamic response, complex parameter tuning process, and poor power quality under nonlinear loads. As a promising alternative, model predictive control appeals to much attention in recent years. And here is some of most widely applied model predictive controls, such as finite control set model predictive control, deadbeat control, and modulated model predictive control. For these control strategies, it is essential to establish the accurate mathematical model of the system. For example, here gives the continuous domain state space model of the above circuit. The state variable includes the voltage on filter capacitor Vf and the current flowing through the filter inductor If, and the control inputs are the output current I0 and the switching voltage Vi. Further, it is discretized using the zero-order Hall method, which conforms to the discrete nature of the digital processors. And the working principle is quite intuitive. We just need to evaluate each Vi for all possible switching states through a predefined cost function. Moreover, it provides the ability to involve nonlinear control objectives and offers faster dynamic response. Here, the widely used cost function is used to compute the error between the sampled voltage and its reference to realize the voltage regulation. The following figures reveal the difference in working behaviors between FTS-MPC and DBC. It is noted that in this case, MMPC is similar to DBC. FTS-MPC only selects one candidate voltage vector as the control input at one sampling period, while DBC chooses a pair of adjacent voltage vectors to synthesize the desired voltage vector. Therefore, the switching sequence for DBC is symmetrical and has 8 segments. But considering the sinusoidal reference when the voltage waveform approaches to its peak, where the derivative of the reference varies rapidly, which still can cause a large error, especially under some low sampling frequency cases. Therefore, this paper proposes a trajectory-based model predictive control strategy. Apart from the 2 target points that set at the beginning and the end of the sampling period, TBMPC also sets extra target points inside the sampling period, like this point, at the middle of the sampling period. By setting these extra target points, we can better track the voltage reference through this cost function, which is defined to minimize the tracking error. First, it defines a straight line between VFK and a new voltage reference for time instant k+1, marked with 2 stars here. And S is the direction vector of this line. EI defines the area between the target point and the line. And we can solve this problem with the derivative of G with respect to S is equal to 0. And finally, the voltage reference is adjusted using these two equations. Before the implementation, we first conduct a numerical analysis. It mainly helps select N, which is the number of extra target points. Here we present a numerical simulation to test the impact of N on normalized root mean square error. As shown in this figure, when N is selected as 2, 4, or 6, it generates a smaller NRMSE. Considering the computational burden, we'd better select N as 2 or 4. And Figure 7 shows the overall block diagram of the proposed TBMPC strategy. As one can see, the voltage reference is adjusted after the electrode variable are sampled, and then it is sent to the predictive model to calculate the optimal control input. And finally, the gating signals are generated through the PWM module. Here, some simulation tests are carried out under different switching frequencies and load conditions to validate the proposed strategy. As shown in Figure 8, when TBMPC is combined with different existing MPC strategies like FCS MPC and DBC, it shows improved performance in terms of smaller THD and NRMSE for both controllers. Moreover, the superiority becomes more evident when the sampling frequency is reduced to 5 kHz, where the THD reduces by 20% and the NRMSE reduces by around 40%. Also, TBMPC provides better performance when a non-linear three-phase load is connected. The last section draws the conclusion of this paper. First, the proposed TBMPC tracks the sinusoidal variation of the reference to achieve better power quality, and the numerical analysis helps find the appropriate number of extra target points. Simulation studies validate the applicability to different MPC strategies and its superiority in terms of smaller THD and tracking error. Thanks for your attention. If you have any questions, please feel free to contact us anytime.